Welcome. This question says a spring is stretched by 4 meters. The spring has a spring constant of 7 newtons per meter. How much work was performed by the stretching force? So let's picture this. We have the spring just been left to its own devices, and then we have the spring that's been stretched, and we know that the displacement, the delta x, is equal to plus 4 meters because I drew it going to the right, that's why it's plus. And this is occurring because there is a stretching force. How much work is performed by the stretching force? So I have that, we'll call it Fs. Could call it the applied force. It's just a shorthand notation for me. And I want to know how much work is done. So find work done by Fs, work done by the stretching force. So let's just think about what we know. What do I know? I know K is equal to 7 newtons per meter. K is always positive. It's always a positive value. When people get a negative value for K, it means they've messed up with their signs on a displacement and a force. So K is always a positive value. And we know that delta x, this stretching, is equal to plus 4 meters in this case because of my diagram. And I want to find the work done by my stretching force. Okay. Well, let's think about this. Let me put some things in boxes because I drew my diagram a little bit big, so I'm a bit worried that I'm going to start getting confused over which is which. So let's have a look. Let's just say, well, work done by my stretching force is equal to the stretching force times the displacement that my stretching force moves through times the cosine of the angle between. And my stretching force is in the same direction as my displacement. So my displacement is there. So therefore I know that this goes to 1, so I can say the work done by my stretching force is equal to Fs times d times 1, and the work done by my stretching force is equal to the stretching force times plus 4 times 1. So, okay, all I got to do is find my stretching force. And yes, I can use action-reaction. I'm going to walk off a cliff now, and I'm going to show you it so you can see it. So I can use action-reaction, and I say, oh well, my stretching force is equal and opposite to my restoring force. That in itself is fine, Fr. And I know that my restoring force equals Hooke's law. So I say, oh, well, in that case then, this is equal to Fs is equal to minus of Fr. So Fs is equal to minus of, and my restoring force using Hooke's law is minus K times delta x. And it's gorgeous. I know Fs is equal to minus makes plus K delta x. K is equal to 7 times delta x is equal to plus 4. So Fs is equal to plus 28 newtons. And then I substitute in. I am walking off a cliff. I'm just deliberately walking off a cliff here. So that equals the work done by my restoring force is equal to 28 times 4, 28 times 4, which equals 80. 3 is 24, 4 it's a 32. It would be 112 joules. And I look over here and there's not 112 joules. There's a 56, but they're all about, much lower. And so I clearly made a mistake. And what mistake did I make? Well, the mistake I made was that I just pictured this thing at the end. And of course, my restoring force, although it's always equal, although the stretching force is always equal to the restoring force, position by position, when I only had a little bit of displacement, I only needed a little bit of stretching force because I only had a little bit of restoring force. And it turns out if I plot my Fs versus Fr, I'd find that it would be a linear relationship when Fr equals 1, Fs equals 1, when Fr equals 2, Fs equals 2, when Fr equals 3, Fs equals 3, and so on. And the work done, of course, would be well, now let's draw another graph, and we can say, well, Fs in relationship to the position x, and I'd see that as my position increased, so my Fs would increase because Fr is related to position. Well, this stretching, which depends upon the position. And I see, well, then the work is equal to the area under the triangle. And can you see what I should have done? Rather than taking the final value of Fs, I should have took the average value of Fs. And because it starts at 0 and ends at the maximum Fs, the average value is half of that. I did not. I'm going to quit that. So what that means then is I should have used, rather than 28, I should have used 14 because it's the average value. And then I say, well, Fs is equal to 14 times 4, which equals actually 56 joules. And their answer, 56, is there. And that is the right answer. And this methodology would work, but it's a bit of a complicated methodology. So I'd like to show you another approach. And the other approach is using the work energy theorem. So I'd say, oh, well, let's find the work done by my spring force, by my stretching force, is equal to using, and the work done by my stretching force is equal to the work done by my stretching force is equal to the work done by my the work done by my stretching force is equal to my change in my spring potential. As I stretch this, I'm putting energy into the system, and so I can say the work done by my stretching force is equal to the work done by my spring potential. So the work done by my stretching force is equal to 1/2 times k times delta x squared. So this is going to be equal to 1/2 times k, of course, is 7, times my delta x squared is plus 4 squared. So work done by my stretching force is equal to 16 times 1/2 is 8, 7 8s are 56 joules. So what I'm trying to do is just illustrate to you the fact that getting the right approach can save you a lot of work, or it can involve a lot of work. There's nothing wrong with doing the force simply saying that the work is equal to, my definition of work, the force times the displacement times the angle between, and then recognizing that I don't have the value for the stretching force, and so trying to find the stretching force, and then I've got a conceptual issue which I must realize that the stretching force is not the value of the stretching force once the job is done. It is the average value of the stretching force in doing the job. And because the stretching force depends directly on extension, and because extension, it will go linearly with extension. Therefore, I can say, well, okay, then the stretching force is the midpoint between 0 and what it ends up finally being. So I can, rather than using the maximum value of Fs, I use the average value of Fs, which is, rather than 28, using 14 newtons, and then multiply that 14 newtons by the displacement, and I'll get the true answer for my work done. There's nothing wrong with that. It just involves a conceptual point which might not be immediately obvious until you practice doing a lot of these things. It's a subtlety to some extent. Whereas if I say, oh, well, the work done is on this spring is changing the energy of this spring, work energy theorem, and the energy that the spring holds is spring potential energy, and I know an equation for that. Spring potential energy is a half K times my extension or my compression squared. So let's see where that takes us. So work done is simply equal to half K delta X squared, and the answer falls out. And I think part of the ability to be able to see where you are is just, it's a little bit unfair, but it's just how much time you spend on these problems. And you can recognize, oh, this is often easily solved by using work energy theorem. So I think it's training yourself. It's training yourself to be able to see the different ways you could approach the problem, and recognizing that sometimes some are easier than others. So there we have it.